Okay. So we find f of a plus h. We're just plugging a plus h in for x, right? Okay, so it's going to look like minus 5 a plus h's. Okay, plus then 4 a plus h's squared, right? Now we should be able to expand that. Okay, should be able to expand that. So it's going to be 3 minus 5a minus 5h. Plus then, okay, so I'm going to do this all at once. I'm going to square a plus h, and I'm going to multiply by 4. So squaring this, give me a squared times 4 will be 4a squared. They binomial, so my o and i's here would be ah and ah, so it's going to be 2 ah's times my 4, which is 8 ah's. And then last times last would be h squared. I'm multiplying that by 4, right? So 4h squared. Is that doable? Okay, so that's part 2. Part 3 says you're going to subtract them in this order. You're going to take 3 minus 5a minus 5h plus 4a squared plus 8ah plus 4h squared, and you're going to subtract that one there. So it's going to be minus 3 plus 5a minus 4a squared, right? And I'm going to subtract the quantity, so I need to distribute my negative through. And then it's putting it all over h. So that looks pretty messy. A lot of nice things happen here. What's going to happen with that 3 and that negative 3? Wow. Cancel. What about this negative 5a and that positive 5a? Wow. What about this 4a squared and this negative 4a squared? Wow. Cancel out. So the only thing I'm left with then on top is negative 5h plus 8ah plus 4h squared, right? And on the bottom, I'm left with h. Well, something nice happens there as well. That and that cancel, that and that cancel, and then that one and that one cancel, right? So does that leave me negative 5 plus 8a plus 4h? Okay. So that is your answer. Okay, so that's college algebra. You can do that. You've mastered the concept in college algebra. Okay, just evaluating functions. Okay. Now, let's talk about how this is used and what this is. Okay. Making some vocabulary connections from geometry. If I have that circle and let's say I have the line x equals a. So we have that line right there. Does anybody remember what that line is called, or any line that passes through a circle 2 times is called? S. Do you remember what this word is? It is a, so this segment here, try to get the color right. Huh? No. Does anybody remember the vocabulary word? Oh, okay. So which one's the secant? Is it the red one or is it the line? Well, your point is there's both out there. All right, so the red one is called a chord. Okay? A chord is a segment whose endpoints lie on the circle. A line that contains a chord is called a secant. So that black line that's passing through my circle 2 times is called a secant. Okay? Now, here's the thing. You guys didn't think that stuff was all that important in geometry. Nope. Okay. Well, it's going to be important in this class and the next one. Okay, that's why I spent time on that vocabulary with you. As I move that secant in the circle, what does it quickly become? What kind, if I can get that to be 4, what kind of line do we call that black line now? Instead of intersecting twice, it intersects once. It's called a teeth. Nope. Tangent. Okay? So that's a tangent line.
Well, we're going to use sine, cosine.
Okay? Well, there's a relationship with that, and that's, we'll talk about that in trig. Okay. So, that's what we learned in geometry about circles. Let's talk about it with just general curves. Okay? Because it doesn't just have to be a circle. If I have these 2 points here, okay, A and B, would you agree that that blue line is passing through the parabola 2 times?
Yes.
So what do you think we call that blue line? A secant. Okay? Now, here's the thing. We are interested, and I'm going to put that point A over here at an x value of 1. All right, so in calculus, we're interested in being able to find the slope of that parabola. Okay? So here's my thought. Okay? If I am on that parabola at this point here where my cursor is, okay, and kind of put yourself as you're walking on the inside of that parabola. You're kind of going uphill a little bit, right? But it's not that drastic. But put yourself over here where my cursor is. Now you'd be walking, and we're moving left to right. Now you'd be walking downhill, right? And we've all walked downhill before, and you have to your feet have got to move faster, right? You're going, it's pretty steep, so you've got to go a little bit quicker, right? Does that make sense? You got to move your feet faster. But if I'm down by the vertex, I shouldn't have to move my feet as fast. It's a little bit slower, right? So what that means to us is that as we move along at different x values on that curve, the slope or the steepness, the rise and run, the change in the y value or the change in the x value changes. Does that make sense? Okay? Think about this. If I were to put that line right there, okay? If you were standing on point A on the parabola, would you be standing at the same point A on the red line? Okay? So if you can, now I like to put myself there and kind of use that argument as how would I feel standing on that line, or walking up that line at that point, or maybe I'm on a roller coaster and I'm at that position. How would I feel? Would you feel the exact same thing there on that red line as you would there on just the parabola? And you would. Physically, you would. It's a physical fact that you would. So the slope of that red line is the slope of that parabola at that spot. Does that make sense? Because when I move that spot, that slope changes. But here's the idea. If I want the slope of the parabola at A, then I just find the slope of this red line. Does that make sense? But if I want the slope of the parabola there, I'm now going to have to find the slope of that red line there. Does that make sense? Is that a different red line?
Yeah.
So it's a different slope, right? Yeah. Okay. Now here's how we do this. How do I, with slope of a line, how do I do that? What do I need? How many points?
2.
You need 2 points. Okay. A tangent line, I only have what? I only have 1. So what we do is we say, nope, not going to do a tangent line, going to do a secant line, because that has how many points? That has 2 points. Now, would you agree that that slope right there of that secant line is probably a bad approximation for that red one is what I'm trying to find, right? So the idea here is that we're trying to use the blue one as an approximation for the red one. Does that make sense, everybody? Okay, so here's how we do this. How can I make that blue line be more like the red one? Do I take this point here and slide it closer to A? Okay. So now remember to find the slope of that blue line, I'm taking the y values of A and B, subtracting them, dividing by the x values, or the difference of the x values of A and B, right? Does that make sense? Okay. Now, eventually we want that distance to be very, very minimal. Because when that distance is very, very, very small, the red line and the blue line almost overlap, right? Okay. So here's the idea. This distance right here, from 0 to here, okay, which would be the x value of A, right? We're calling that lowercase a. Does that make sense to everybody? Okay, lowercase a. So let me just rename this ordered pair real quick. We'll call this, let's see here, F. Let's go A, comma, F of A. So that is the ordered pair for that point right there. Does that make sense? So this distance here is A, and this vertical distance here then would be F of A. Okay? Well, to get to B, don't we go from A, lowercase a, and add a little bit to it to get to B? Does that make sense? Now, what I'm adding to it is this distance here. Okay, well, I'm going to define that distance as h. So let's call this ordered pair A plus h. So then the y value is f of A plus h. And I'll have parentheses. Does that make sense to everybody? How would you find the slope between that point and that point? Would you take this y value minus that y value? That make sense? Yeah. Okay. So f of A plus h minus f of A. F of A plus h minus f of A. That make sense? Okay, so this is just a y2 minus y1 up here. Well, if I want to find the slope then, after I subtract the y's, when I subtract the x's, A plus h minus A. What's A plus h minus A? Just h. Okay? So when I said you've seen this thing, you've seen the difference quotient many a times in your math careers, it's because it's just the what formula? We just subtract the two y's divided by two x's. It's the slope formula. Okay? This is y2 minus y1, and this is the x2 minus x1. Okay? Simplified. So, going back to this, if we can make that distance h, so this is the distance h right here, right? If we can make that very, very, very small, okay? And what we talk about in calculus is that we want to make the distance between these 2 points, A and A plus H, we want to make that what we refer to as infinitely small. Okay? Would you agree that the distance between the 2 points is very small right now? They're almost on top of each other, right? So that zooming in process, I kind of shown that those 2 points are separate. Okay? But now we see the blue line and the red line are almost 100% overlapping, right? But now what we can do, because of the fact that we do have an A plus H, we have an A, we have these ordered pairs, we can do the subtraction, we can find the slope of that blue line. And what we did then, algebraically, guys, right here, is this is the difference, okay, because we did this, right? We did f of A plus h minus f of A over h. We found the slope, okay? Now, the idea is that distance h, this distance between C and D here, when it gets infinitely small, it's really close to what number? Okay, remember h. Let's go back to this. H is this distance here, right? Okay, which is the gap between these two, the horizontal gap between these 2 points. When those points get like that, what is that distance almost equal to? 0. So in calculus, we use this concept. We call it a limit as h approaches 0. So as that distance is getting closer and closer to 0, we ask ourselves this question. What does 8a plus 4h look like? And basically what a limit is the idea, okay, what is the y value when h is getting really, really close to 0? Well, if h is really, really, really close to 0, this thing pretty much goes to 0, right? So I'm left with negative 5 plus 8a, or 8a minus 5, how you want to write it. Okay, so remember what a was. A, lowercase a was the x value for that point there, right? Okay, so let's do that. I'm just going to switch around things here. Object properties, let's look at name and value here. So the lowercase a right now would be 1. Does that make sense to everybody? If I were to find the slope of the green curve at that point, capital A, all I have to do is plug in now 1 to this expression. So if I plug in 1 right here, 8a minus 5, so 8 minus 5 would give you what? 3. And now if I found the slope of that line right there, see the slope's 3? Okay. Give me another x value you want me to try. 7. This might be kind of a pain in the butt. Now we should be able to get there. All right, so now a little bit of rounding. Oh, there we go. So I do 7, I should get a slope of 51. Does that make sense? Plug 7 in this thing. What's 8 times 7? 56 minus 5? 51. Okay. So do you see this is a formula? This is a formula for finding the slope of this parabola no matter where I am on the parabola. Okay, if I'm at 2, okay, if my x value is 2, the slope over here says 11. We'll plug in 2 to this thing. What's 8 times 2 minus 5? 11. Okay, so when we're doing this process here, in college algebra, what that is setting us up for is to have the ability to find the formula that gives me the infinite number or infinite different slopes of any curve at any point. Does that make sense? Okay. When you work inside calculus, there's 2 concepts. There's slope and areas. Okay. This is the first section of calculus. The first kind of half of a calculus course that you start dealing with. Is that all right? Okay. So if we've got opportunities like that, guys, to kind of foreshadow and see where we're going to take this stuff, I want to do that. Because I think if you see where this stuff is going, it then makes it's more meaningful now, right? Does that make sense?
Yeah.
Okay. If I don't think I'm ever going to see that again and never need that again, I'm probably just going to blow question number 21 off and be done with it, okay? But if I know that is going to be like the first 2.5, 3 months of calculus, and I'm going to work with that thing on a regular basis in that class, I should probably maybe take it a little bit more serious, okay? So if we have those opportunities to talk about that stuff, I'm going to, okay? Getting back then to working with functions. So why is that a function question. Well, it was asking us to evaluate a and a plus h and that kind of stuff. But when we get to calculus, we're going to be interested in looking at a function, finding its slopes and all kinds of stuff at infinite points. But in order to do that, we need to understand what the domains are for that function. So it's kind of a good kind of prelude into working on this stuff right now. Yesterday, I believe you guys, we kind of haphazardly went through the first two examples because we're running out of time. So I want to rehash those. But what we said yesterday is that if we can recognize that we have a function that's polynomial, okay, ultimately a polynomial is anything that is a series of monomials attached together, plus and minuses, in which the exponents are positive whole numbers. Okay? If you've got anything like that, then your domain is all real numbers. And as we work through the year, guys, every single chapter is going to be a different series of functions. Our first assumption is that every function that we come across the first time is going to have a domain of all real numbers. And then we work through the algebra to see, okay, well, which of those all real numbers don't work? Which ones do we need to kick out? Okay? So, every polynomial domain is all real numbers, and then as we work through algebra, there's nothing we ever need to kick out. Okay? So that's the first thing up there. The other two are what we call restrictions or conditions, and they incorporate algebraic rules that we need to abide by. First one is division by zero. You ever come across a function that has division in it, it's called a rational function, and you can never divide by zero. So those would be domain issues, because what a domain issue is when I take a particular x value and I plug it in, and I don't get a defined value back. I don't get a numerical y value back that I can actually plot. Okay? So, for instance, if I look at example 2 there, -3, if I plug that into that expression, I'm not going to know what I get back, right? 1 over 0, I don't know what that is. That's undefined. So that means then -3 could not have been an x value to use. So we need to make sure that we make note of that. In order to do that, when we have division, basically to figure out which x values do not work or which ones do not provide us a defined y value, is we take that denominator, we set it equal to 0, we solve that equation, or sometimes maybe, so that equation might be linear, might be quadratic, might be cubic, whatever, we might have to do some factoring. At times, that equation might actually be an inequality. Example 5, it'll be an inequality. But what we have to do is solve that, okay? And that will give me then the values that I cannot use, okay? If I incorporate a square root in my function, okay, we know that we cannot take square roots of what kind of numbers? Negatives, okay? So what we do then is we take our radicand, and we say that our radicand has to be greater than or equal to 0. In most cases, probably 99% of the cases, that's what we'll do. Okay. Example 5 again kind of throws a wrinkle into that, but we will set our radicand greater than or equal to 0. We'll solve, and then whatever we solve for, that will be our interval. That will be our domain. Okay. So that's what we set up there in that section that says restrictions. Kind of while we're talking about square roots, what's the square root of a square root? What's another way of identifying that? It would be a fourth root, right? So if I can't take a square root of a -1, can I take the square root of the square root of -1? No. Okay? So my innermost function there would have been square root of -1. If I can't evaluate that, well, there's no way that I can evaluate the square root of that. So a fourth root of a negative is impossible to do. Does that make sense? Okay. Can I take the 6th root? Nope. Can I take the 8th root? Nope. What are we seeing about 2, 4, 6, 8? Even numbers. You cannot take a root, an even root of a negative number. Okay. But I can with I can with odd roots. Okay. So if it's a square root, 4th root, 6th root, 8th root, whatever it is, it's the same process that we use for a square root. Okay? If it's a cube root, you don't kick anything out. because you can take the cube root of negative values. Okay? So those are things that we're going to see and address as we move through these questions in your homeworks. So this first example. Did we do this one yesterday? We talked about it a little bit, didn't we? We recognize we got a square root here. Okay? And we started thinking, okay, I'm not allowed to take square roots of negatives. So you can kind of do a trial and error type thing. Say, well, what numbers do I need to plug in here so this thing turns into a negative? Okay? But the more complex that this expression becomes, the harder that process is. So the safe technique is just to take that thing, take that radicand, and say, well, we need to make that thing positive or zero. Positive or zero. And that's how we do that. We take x plus 1, we say it's got to be greater than or equal to 0. And any limit is taken, that takes all the guesswork out of seeing what my domain needs to be. I solve that. And I get x has to be greater than or equal to negative 1. Okay? So here's the idea. We started with the assumption that the domain for this function was all real numbers. So this entire number line, negative infinity to positive infinity. And then we realized, well, there's some square root issues. So numbers like these that I'm erasing would actually give me a complex number, right? Or an imaginary number. So we can't use those. So we get to that. But that one I can use, right? Negative 1 I am allowed to use. I would get 0 here. Square root of 0 is 0. And I can use all these numbers to the right, right? So we need to write that then in interval notation. And that would be the solution we're looking for. Does that make sense? Okay. The root function, and this is going to be the same for root functions, square roots, fourth roots, whatever you want them to be. So I'll just do square root of like x. I'll just go plus a right now. So what we did is that x plus 1, we see now that the x values, remember what we're doing here when we find the domain is we're trying to find all the possible x values that point A would have, right? Does that make sense? And we're seeing here that the first one would be negative 1. And then I move to the right, correct? As I go to the left of negative 1, you see that it's undefined, right? It's not graphed over there. Okay? But what this thing here does to our square root, okay, if I started at 0, so square root of x, you can see how that gives me kind of a starting point, doesn't it, for my curve? If it's plus 1, my starting point is over here at negative 1. If it was plus 2, my starting point is going to be over here at negative 2. So we see that when we set this thing greater than or equal to 0, it's going to give me that first point, that first x value of my curve moving to the right then. Does that make sense? Okay. As we start working later on with transformations, we might put a negative here, and we see that gives me a y-axis reflection. Now, if I set that thing greater than or equal to 0, it would give me the inequality to say we're going to use a domain that has negative numbers all the way up to a positive 2. That kind of makes sense graphically what's going on there? Okay. Now, with root functions, they might occasionally ask you, well, what is the range? So we know the domain right now is negative 1 to 0. They might ask me the range, and this is because I can actually, with a root function like this, I can just kind of plug into my domain values and get my range out. So if I plug in negative 1, right here, don't I get a range value of 0? Okay, so, and then as I plug in values that are to the right of that, if I plug in like 99, don't I get 10 back? That make sense? If I plug in 9,999, don't I get 100 back? Okay? So what we'll see here is that the range actually goes to infinity. Okay? The reason for that, the logic for that, is graphically speaking, I go back to okay, we can get a y, but we talked about that in behavior yesterday, is this thing moving to the right. All my y values are going to be incorporated at some point. Okay? It is hard, if I were to look at, let's just say if, let's go x is between -2 and 3 for x squared. Okay, so my domain for this thing here, guys, would be between -2 and 3. Does that make sense for that graph? Okay, so domain, I wish I had, the way I can write, it's just kind of, I want to write on this screen, but it's a pain in the butt to use the tools that I've got. Give me a second. All right, so this domain is going to be -2 to 3, okay? And if I ask you what the range was, okay, knowing that this function is x squared, can I just plug this in and say, well, the range is 4 to 9? Can I do that? Is the range, so all I do is I plug these endpoints in, right? Is my range here 4 to 9? No, my range is actually 0 to 9, right? That makes sense, everybody? So that substitution process that you might kind of get accustomed to with square roots, okay, does not work for all functions. There's really not a real nice defined way to find the range algebraically. There might be some, kind of like this one, some special cases that you can substitute. There will be, when we talk about inverse functions later on, maybe a better way to do it. But right now, the range, a lot of times, if they're asking you for it, you can either substitute because it's just a convenient special case, or you're going to have to graph it and look at the graph. Does that make sense? Okay. You're going to find out in your homework when they ask you domain questions, usually they don't ask the range, and that's the reason for them not doing that. Okay. So let's look at this bottom one, example 2. Okay. Example 2. We've got division. Division is a issue. It's the restriction. So what do I do? 3 plus x, what do I set that equal to? Set it equal to 0. And go ahead and solve that. Now again, understand, guys, the equations here that we're generating when we do this, that's not a hard equation to solve, right?
Yes, sir.
Now as you work in your homework, that might be a little bit more difficult equation. There might be a variable term that is like 2x. There might be an x squared or something like that. But whatever equation you generate there, you have the prerequisite skills to solve. Okay? So you get x equals -3. Now the idea is, when I solve that equation, I'm actually finding what x is not allowed to be. What x is not allowed to be. So remember, as we see each function, our initial assumption is that the domain is all real numbers. -infinity to +infinity, right? We just said, no, x is not allowed to be -3. There should be a hole there. Okay? So as we write this thing in interval notation, remember we'll take our number line, and we're going to start dragging this thing through. So what would be the first x value I come in contact with? -infinity. Okay? And I'm going to get up to what number that poses a problem? -3. And that says we got to exclude it. So we do something like this, correct? That tells me I can get just to the left of -3. I'm not going to include it. Now I want to jump over it. I want to be just to the right of -3. Well, just to the right of negative 3 would look something like this. And then there are no other issues as we go through, right? Remember that right there, that notation where I've got a number, a value, parenthesis, union, parenthesis, the exact same value, that is the effective way in our intervals to kick out a number. We wanted to kick out negative 3, and that's how we have to do that. Is everybody on the same page with that?
Yes, sir.
Okay. Example 3. Do I have to do any work?
Nope.
Why not? What's the assumption we make about the domain?
All real numbers.
All real numbers. And then I look at that, and I ask, okay, are there any restrictions? Is there any division, or is there any square roots or even roots in general?
All real numbers.
No. So all real numbers. So nothing gets kicked out of that initial assumption. So that domain would be all real numbers. Okay? Example 4. The only way that I'm going to get a y value back, or a k of x value, an output back, is if I can evaluate the numerator and get a number in the numerator, right? And evaluate the denominator and get a number in the denominator, and then take their quotient. Okay? So when I find the domain, I need the domain to be defined for the numerator and to be defined for the denominator. Okay? So for instance, does 5 work in the numerator? 5 minus 3 works, right? I can take square root of 2. Does 5 work in the denominator? No. It has to work in both. So 5 would be a number that we get rid of. Okay? Think about negative 1. Does negative 1 work in the denominator? Yeah, I get negative 6 back, right? That's not 0, so it's okay. It works. Okay? Does negative 1 work in the numerator? No, I get 2i back, right? That's a problem. Okay? So there are numbers that work in the top one but don't work in the bottom one. There's numbers that work in the bottom one but don't work in the top one. And when I say work, I mean they don't provide me a defined output. Okay, for those individual top and bottoms. We need numbers that work for both of them simultaneously. Okay, using that intersection idea if we're talking about graphs. So, first thing you're going to do is you take your numerator, and because it's a square root, you're going to say x minus 3 has to be greater than or equal to 0. Again, an inequality that is not difficult to solve. So right now what we did is we made the assumption, that we can first start with all real numbers. But this here tells me now what you have to do is restrict those real numbers. Now you can only work from values greater than 3 or equal to 3. Does that make sense? Okay. But if I remember, I've got x minus 5 here as well. So I take my denominator, set it equal to 0, solve for x, and remember that's really saying what values x is not allowed to be. Doesn't it pull out one of these values off that number line and basically erase it? Okay. So now what we have to do is take that graph and convert it into interval notation. So what's the first value you come across?
3.
3. You include it, right? What's the next number I run into a problem with? 5. So 5's got to get kicked out. So the way we kick a number out, you write the number down, parenthesis, union, parenthesis, same number. And then I'm going to go up to what? Infinity. Okay? Now, if you wrote 3 to infinity, and you wrote that as an answer, you have an infinite number of answers correct. But if I have one bad egg in there, like 5, that makes all those infinite answers actually incorrect. Does that make sense? Okay? Now, a little twist here is example 5. Okay? When I look at example 5, I'm trying to think about what are my requirements here. I cannot take square roots of what kind of numbers? Negative numbers. So I would take that square root, look at the radicand, and say, oh, cannot be negative numbers. So greater than or equal to 0 says 0 or a positive number, right?
Yep.
But if I solve that, I got x equals negative 1/2, or x is greater or equal to negative 1/2, right? Well, if I plug negative 1/2 into that radical, what's 2 times negative 1/2? Negative 1 plus 1 would be 0. Square root of 0 is 0. Can't divide by 0. So what am I not allowed to use? Negative 1/2. So I cannot have the equality here. When you get a radical in your denominator, you have to remind yourself that you cannot have equality. So doing that, taking that equality part out, kind of ties in the two parts that we did in example 4. Okay? If I go ahead and solve this, then x is going to be greater than negative 1/2. So then negative 1/2 to infinity would be our solution. Okay? Now, as we work through this stuff, guys, you might see an example. Let me come over here real quick. If we've got, let's just say f of x is equal to, let's just go 2x over x squared minus 5x plus 6. Okay, we have division, right? That thing is posing a problem. So we take that, x squared minus 5x plus 6, and we set it equals 0. What does this algebra tell me I have to do? I need to factor it, right? So that gives me x equals 2 and x equals 3. But remember, it's really what x is not allowed to be. So I'm not allowed to have 2, I'm not allowed to have 3. So number line-wise, I'd have an open dot at 2 and an open dot at 3, but everything else would work, right? So I'd go from negative infinity up to 2, union 2 up to 3, union 3 up to infinity. And you see this here, this interval right there, incorporates those numbers. This one here incorporates those numbers. This one here incorporates those numbers. Or I guess describes them. Okay? So regardless, I know the examples we did, the denominators are a little bit simpler. The radicands were a little bit simpler type problems. But whatever you find yourself with underneath the radicand, or whatever you find yourself in the denominator, when you set it greater than or equal to 0 or not equal to 0, like this case, you should have the tools to solve whatever equation is presented to you. Okay? There is a new assignment in WebAssign. It's not due. Right now I got due on Thursday, I think. We'll hit a couple more of these tomorrow. We'll see where we're at with finishing that up. The latest that I would push that back would be Friday. The other assignment is due tomorrow. 2-1, part 1 is due tomorrow. Make sure you finish that up. Towards the end of the week, my plan is, after seeing enough of these, to give you a quick quiz over finding domains of functions. Okay?